Okay, so let's get some representation of our acceleration, velocity, and position um, for our rotation. I changed these variables right here, and the way we're going to do that is we're going to represent acceleration with a small sphere, about 0.25, and I changed this to match so they're both at 30. So that was this is our position sphere. We're going to leave that large. And then we want a velocity, and we want that about half size. So we'll be able to tell the difference between the three. Okay, so now we just need to pass out our velocity plane. So we have our orientation plane, and then we have the mover's orientation plane of velocity. Okay, so let's try this. And there we go. Okay, so now you can see we have acceleration, which is just slightly off of our z-vec, and then we have our velocity, which is slowly growing. It's growing at a constant speed based on the acceleration angle. And when I say angle, I mean the angle between our orientating vector and our z-axis, our world z-axis. So you can see that this is growing, and then the position is growing at a speed. So for each moment in time, it's moving this far between the velocity and the z-axis. So that should be a handy way to represent for you to see how these are related. And I mean, it's the same way that we did for the location and everything, but yeah, so from 22 to 23, the position changes, or the orientation plane rotates by an angle of between the velocity and the z-axis, and then the velocity changes by an angle between the acceleration and the z-axis, which is really small. So we'll set it up to go again, and that covers the rotation and orientation, and hopefully this will be a pretty firm foundation for us to use in the future.